And I encourage, the rest of you to turn your camera on so that you can actually meet each other before we can physically meet. I have emailed student services to book a room for our week 4 after Canberra Day lecture, and they say there should be no problem. So hopefully we'll do that soon. Oh, thanks, great. I would say, well, silver lining of actually us talking to each other on Teams is that I do get to, I guess, like see your names. When we're in person, I feel like I'm going to be hopeless with the many of you. Right. Thank you for the camera appearances. So brief announcements is basically, right, we'll have 2 lectures next week, and then the Monday after that, we will have a break enjoying Canberra Day. It's usually sort of as the end of summer in Canberra if you're new to Canberra. And for assignment 1, we will do a walkthrough after the main content of this lecture. And a couple of things we talk about in this lecture will help. So let's just talk about it then. And you can ask any questions you might. So Alex Owen, who have contributed his lion's share to making the assignment, will also be joining us. Then. Okay, so let's dive in. The first part of this slide was, right, so this is the content we covered on Monday. One of the main outcomes we got back was what's called the normal equation. And with regularizers, with hyperparameter lambda. Today we're going to build on what we learned and do some more math by taking a Bayesian view of what linear regression can look like. So I would not lie or hide from you the fact that if you have seen the slides, by the way, the slide was also updated in the last half an hour or so on Piazza. So if you want to hop there and grab a copy, by all means do that. We're going to venture into a bit more of matrix manipulations, especially Gaussians. It is, again, something that will take a bit of time to sink in. So those will be mainly in the parts of conditional Gaussians. We'll see basically multidimensional Gaussian a variety of different ways. And then we're going to use them to derive Bayesian regression and the predictive distribution and see, like, if we interpret essentially regression, linear regression in terms of conditional Gaussians, Gaussian priors, and so on, what does it look like? One of the results from this is we will, like, after we've done all of this hard work, we will be able to see that the Bayesian view of regression and regularizing has inherent connections with each other. And then we're going to talk about 2 things which I think are useful and I enjoy them. One is the view of estimating distributions in high dimensions and why you may not want to do that sometimes. There are technical reasons, which is quite good. And the last thing is information theory. In particular, I love, information theory is such a cool mathematical concept that has many real-world implications about uncertainty and how we encode information. So I think it's a great thing to learn if you haven't taken the information theory class in the computer science school. The other thing is that some of the metrics used in here are very widely used in machine learning, especially Chao Divergence, which you will encounter and manipulate in assignment 1. And later on, when we talk about proximate inference and EM, you'll also see it again, right? So before we jump to conditional Gaussians, there is this term, I suppose, is called conjugate prior. That's worth knowing. So we know that if our data is X, our parameters are called W. P of W can be called the prior distribution, right? So in the frequentist view, when we do maximum likelihood, we don't really assume W is anything. We just estimate W from the data. But if we do know W is something, such as the magnitude of W is not too big, or we may know that, like, for example, some dimensions of W might have larger values than other dimensions. There are mathematical ways of specifying this knowledge, which can be encoded in this prior copy of W. So having an analytical expression of P of W allows us to estimate what's called the posterior P of W given X. And conjugate prior refers to the fact when the posterior of W and the prior of W are the same kind of probability distributions. Okay, and so this has, right, so basically what these tables mean is that, for example, P of W and P of W given X will be distributed sort of according to a certain form. Like if we're doing coin tosses or dice, like once or multiple times, the conjugate prior is beta. So the data likelihood P of X given W is Bernoulli binomial. The prior is beta distribution. If the likelihood is multinomial, basically choose one among more than two possibilities, then the conjugate prior is what's called the Dirichlet, which is a distribution over a vector that sums to 1. So moving to the continuous random variables, it's worth noting that, for example, if we have exponential distribution or normal distribution, the conjugate prior, well, as likelihood, the conjugate prior gamma or normal. So if W only represents the mean parameter of Gaussian, then the conjugate prior happens to be also Gaussian. But in general, the likelihood and prior and conjugate prior are not the same form. On the other hand, as you will see in Assignment 1, this is another benefit of the exponential family. Basically, if the prior is in the exponential family, the conjugate
Sorry, Lexing, I think you're muted for some reason.
Okay. Let's see. I hope you can hear me. Yes. Okay. Right. Let me restart the screen share. So I just got a prompt from the iPad that I'm both writing on and talking to, that it got dropped off from ANU secure Wi-Fi. And I hope this is going to fix itself. Right, great. It's showing me that I'm multidimensional Gaussian. We're good to go. Thank you for the patience. Hope ANU secure doesn't go off again. Otherwise, I might have to figure out a way to connect this iPad to wired internet. Anyway, so on the top right is the familiar form of multidimensional Gaussians, where X is a vector, mu is a vector, covariance matrix, big sigma is a matrix. Since we're talking about like two vectors, the parameter W and to essentially concatenate them as a big long vector in the context of what we're talking about. We'll eventually want to call one part of it W, the other part X. So each part has a mean vector. We call them mu. Like we just now call the two parts A and B, subscript A and B. So therefore, U is a concatenation. Mu is a concatenation of mu of part A and mu of part B. So that should be straightforward. What is slightly less straightforward is how the covariance matrix. Right. So in here, what this means. So for those of you who have manipulated lots of multidimensional Gaussians, you can probably just, go make a cup of tea for a couple minutes. For a lot of people, especially if you have gone through the CS curriculum, I don't know how much of this is in MML. People can leave me a comment. Oh, right. So where did audio cut off? Conjugate prior or this particular slide? Right, you can tell me on the chat, and I can try and make it out. Basically, this is the covariance matrix for the A part. Let's say this is the covariance matrix for the B part. So if we think about matrices as just generalized as numbers, like if we think of this sigma AA as the variance for the vector random variable XA, then these two sort of non-square matrices are the covariance between the A part and the B part. Okay, around conjugate prior. Let me go back and summarize the gist over there, and then come back. So the idea of conjugate prior, so I started this slide by saying we care about the prior distribution of parameters W, and we also care about what's called the posterior distribution of W rather than the single point estimate or maximum likelihood estimate. So we wonder what probability of W given X is if we have some way of specifying the prior knowledge of the P of W. And conjugate prior is basically this class of prior and posterior distributions, basically P of W and P of W given X, that falls into the same parametric class. That makes essentially doing, I guess, manipulating distributions mathematically easier. This is also to say that the conjugate prior, basically when it says conjugate, basically prior and posterior have the same analytical form. It does not usually have the same form as the likelihood. I ended this slide by saying this may look abstract and it will get a lot concrete when you do assignment 1, question 2. Basically, you will show for all exponential families, including exponential normal, multivariate normal, and many other distributions we encounter, the conjugate. If the prior is exponential family, the posterior is also exponential family, which is quite nice. And these, for example, like part of this table is just special cases of that. So I hope that helps. And we're going to basically use multinomial Gaussians, or assume that prior distribution are Gaussians for linear regression. And we're going to go through some of the mechanisms of reasoning about multivariate Gaussians and conditionals of Gaussians in order to establish the Bayesian view of linear regression, right, so to speak. So we can, well, if we partition the multivariate Gaussian, like the random variable, into two parts, we can partition the Covariance Matrix into these 4 parts, right, 2 by 2. We can say intuitively visualize them like this. You may ask, why do we need this? So we have the big sigma and big lambda. So the big lambda is called the precision matrix. It's just sigma inverse. Right, the reason that we need essentially the 2 different notations for the same thing is that, well, matrix inverses are tricky objects, and sometimes it's a lot more convenient to write it in one or the other. So for the next hour, we will be staring at precision matrices and covariance matrices for quite a bit, so bear with me. So for now, we just assume that we partition the precision matrix the same way, meaning like the first sort of A by A dimensions is the precision matrix for the first component, and so on. Right. So there will be quite a fair amount of matrix algebra here. We wouldn't go through all the derivation, but I will try and go through most of the intuition that are important in this lecture. So some of this, the behavior of the multivariate Gaussian behaves like, let's say, when x and the 2 parts, xa and xb, are scalars. For example, the joint distribution of P of xa comma xb is this multivariate Gaussian there. And if we marginalize one part, we essentially get a Gaussian, right? So we know that the properties of multivariate Gaussians are the marginals are Gaussian, the conditionals are also Gaussian if we condition one part on the other part. And moreover, if we write the parameters this way, the marginal distribution of xa is simply the mean is mu of a, and the covariances in the A part is simply its own covariance submatrix, which is nice, right? If we condition xa on xb though, things will change. It's no longer that simple anymore, and that's where things get interesting, and that's why we can do inference, or like Bayesian inference makes sense. So let's first again look at cases where xa and xb are scalars in order to establish some more intuition. So here is a general 2-dimensional Gaussian distribution. The contour lines look like sort of a stretched piece are rotating, right? We would say xa is the x-axis, xb is the y-axis. And for example, right, so like sigma AA, or in scalar terms, sigma squares, or like standard deviation of the variable A is here, right? So what does conditionals mean? Conditionals in this picture, in this contour picture, is equal to basically, well, slicing this high dimensional probability volume at a particular value of xb, right? So if given xb equals to 0.7, the conditional distribution of xa is essentially, right, so we imagine this sort of 3D mountain. We cut it at a spot, and then we know that the intersection is still a Gaussian, but now the width of the Gaussian is this green part rather than like this big green part as in the marginal of XA, right? So the what the next picture shows, right? The picture on the right shows essentially the reduced dimension view. It shows the intersection, basically the marginal distribution of XA, which has a larger variance than the conditional distribution of XA given a particular XB. There are some more general results here, such as conditioning always reduces uncertainty. But for now, from this intuitive picture, you can see the spread on XA is a lot bigger on the green contours than on the intersection of the green contour with this red line. All right, we'll get back to this as well. Okay. So now let's try and express them in matrix terms using sigma and gamma. So remember sigma being the covariance matrix, gamma being its inverse, the precision matrix. This is simply rewrite the definition and expanding them into the 4 parts, 4 components. So this slide basically has the intermediate result that we will need to build on. It basically asks, hey, so what is this gamma A B anyway? So to do this, you need a famous quantity in linear algebra that I know a significant portion of you may not have encountered up until now. It's called the Shor complement. It's widely used in machine learning and these related areas, but right, if you haven't encountered it, it basically does this symbolic manipulation. I hope people can still hear me. Some prompt. Right, okay. So it basically does the symbolic manipulation of this 2x2 blockwise matrix and express its inverse in terms of the original 4 components. This is, well, exactly what we need between the sigma and lambda matrices. Let's not try to derive the Shor complement, but let's assume that it's true. Hopefully Matrix Cookbook has an entry about this, but I guess lots of linear algebra books will have this. And we try and just plug it in. Right? So what the Shor complement says is, if we take the inverse of block matrices A, B, C, D like this, there is this important intermediate quantity called M. And the upper right-hand side element of the inverse is simply M. So this basically means, for lambda AA, it's just M. And what you do with that is just you look up A, B, C, D and plug it in. So A is sigma A and so on. And Yes, indeed. Right. So this is a direct application of short complement. For the other parts, you'll need to plug into these equations and simplify a bit. So let's not go there, but instead of it can be hard to get an immediate intuition out of 2.80, but let's look at other equations around it, right? So one useful skill to have if we are manipulating Gaussians, again, you'll be doing some of these things in your assignment and tutorial exercise and so on. In exams, these kind of exercise will somewhere be limited because it takes time to do them and check that they are right? So with Gaussians, it's useful to think of it as a quadratic expression, but it's also useful to sort of try and complete the squares, essentially generalizing the skills that, for example, high school or middle school algebra has about doing this for scalar expressions. Now we're just completing the squares for matrix vector expressions. And like when we're differencing, we can do differentiation by parts, but if we expand the squares, for example, we can ignore the constant part, right? So we use essentially completing the squares trick to try and reason about the conditional distribution of XA given XB. Remember this 1D picture. So let's derive or like partly derive the vector version and reason about whether it looks reasonable or not. So on the upper right-hand side corner, again, are stuff from previous slides that you have seen, but may not store in your head because they're a bit long. So what we do is we take this quadratic form inside the exponential for a vector formed Gaussian. We expand them into the two parts, XA and XB. So the first term is simply the quadratic part involving XA. The last one is the one, same thing involving XB, and in the middle are the two cross terms. Okay, so these are just, I guess, expanding out with the matrix lambda. In that, if we were using sigma, we will be writing sigma inverse everywhere. So, and it's kind of messy because we just saw the short complement. So just write them as lambdas here is a lot simple looking, right? So if we consider a given vector xb, we wonder what the probability of xa given xb is. So we know it's a Gaussian. It's still a multidimensional Gaussian. So from this, if by staring at this long quadratic expression, what we could tell is there is only one quadratic term that involves xa, right? So in the first term, right here. So basically this and this and this, these are quadratic in XA. And this term, this is linear in XA. This is like it's constant as far as XA is concerned. Right, so if we apply the completing the squares trick, we can see that, well, from this general multivariate Gaussian expression, this term in the middle involving the quadratic of the vector of concern is the inverse of the covariance matrix. So therefore, the conditionals, the covariance matrix of the vector xa given b is sigma a. No, so it's lambda a inverse, right? So the precision matrix, right? So the precision matrix of A given B is the precision matrix of A. Okay. You may say, wait, does that not involve B at all? It does not involve values of B. If you stare closely, right, and notice this expression comes from here. Right. This term is here. So actually, it's basically xb is not there, right? So the variance of the conditional distribution. Let me see if it's my problem. Okay. I hope you can hear me without the echo. Right. So the variance of the conditional distribution of vector xa does not depend on where you slice this particular high dimensional distribution, right? So if I draw a red line somewhere else, the conditional variance is still going to be the same. So that makes some sense. Well, graphically it also makes some sense. So now you wonder, where should the mean sit, right? So the mean comes from the linear term. So there are two linear terms. We circled one there, and this term here, right, is also linear in xa. Right, so notice that xb is present, right? So where the mean sit is influenced by like what the value that you're conditioning on, which also makes sense because obviously when we slice at different values of xb here, the mean shifts, right? This red distribution will move left to right depending on where we cut it. I won't try and derive the first line. Let's just try to get some intuition of the second line, 2.75, right? So okay, we start from mu of a, but basically the conditional mean is the combination of the prior mean or the unconditional mean mu of a plus this part. So this is shift in mean. And in this particular picture, so this was mu of a, and for example, if the conditional mean is here, so this is the shift term, right? So the shift term here is described by how far this term is, like how far xb is from its mean, right? So meaning if in this example xb equals 0.7 is larger than its own mean, then the mean of xa, these terms combined is right, actually also larger than its own mean in here, which depend in turn on the precision parameter shift is roughly inverse proportional to the precision parameter, right? So this is like variance in A. So it's sort of when the variance in A is larger, then the shift is larger, and it's sort of inversely proportional to the covariance between A and B. So meaning when A and B has more influence on A, then the shift in mean is larger, which is okay. So these are the intuitions. I hope it helps somewhat. It is sort of an expression that's somewhat long. You're expected to look it up unless you encounter it frequently. So what we just said was the following, essentially. If we condition one part of a multivariate Gaussian to another part, we get another normal distribution where the mean is the prior mean plus a shifter. The marginal distribution is just part of the Gaussian. Right. That's a roundabout way of saying it. And this slide, right, was essentially saying the same thing using the interpretation that we already covered. So where does this lead us? Right, step 2 in this matrix manipulation exercise about multidimensional Gaussians is to plug in, to assume that between these two paths, there is a linear dependency somehow, right? So we're going to use this conditionals of Gaussian's results to ask and answer the following question. So now assume we have X and Y. Again, there's a bit of a notation change, right? So in chapter 2, the multidimensional Gaussians are called X, XA, and XBs, and Ys. But in chapter 3, some of them are called Ws. We'll get there in a bit, right? So let's assume there's P of X, which is normally distributed with precision parameter gamma. There's P of Y of X, Y given X, which is also Gaussian, right? The mean is AX plus B. Okay. This is closer to what we're currently caring about. And there is a separate precision parameter, right? So this remind ourselves in the curve fitting and in the past few lectures, we have like essentially P given P of T given Y of X and W, right? And there's a precision parameter beta inverse. So this L is sort of the vector version of beta inverse. Yeah, so intuitively speaking, so there are two variance / precision parameters. The mean of the two random variables are linked. In the last 10 minutes, the XA and XB are not linearly linked, but in this case, X and Y are linearly linked, and that's the difference. So now we care about, let's say we care about the marginal distribution of P of Y, and also the conditional distribution the other way around. So we use Bayes' rule to try and flip it. Right? The general direction for this using Bayes' rule is try to find the joint distribution of P of X and Y, and then use results from the previous few slides to plug it in. But we can also make some guesses. Meaning, let's see. So because the parameters of X are given, we expect, let's say, the mean of Y should be something like A times mu plus B, like so. Now we're talking about some hunch, right? Which might be somewhat founded by linear algebraic intuitions. And then sigma square of Y, well, yeah, as we said, these are all Gaussians. They should involve both precision parameters in some way. And yeah, so, and the mean of x given y, it should involve all of these parameters, right? So mu, a, b, and maybe even has the precision parameters in it. Same with this. Sigma squares. So let's see what we can do here. So the trick is now we write the concatenated vector z, write out the base rule in log form. Here's another useful trick is to just, when we have a multidimensional Gaussian and things like that, a lot of things become constants. And we don't need to care about them, including the normalizing term in front, and so on. So we just focus on the quadratic term. So because x has a parameter mu and lambda, its quadratic form term is like this, and y's quadratic form is like this. And we complete the squares. Because if we complete the squares in terms of y, we get essentially the margin of y. Right? And if we complete the squares about x using y as a constant, pretending y is a constant, so that will give us the expression of x given y. So in here, this is because x and y given x are these quadratic forms. If we complete the squares for x and y jointly, we get this. Right, so it's taking this and then unrolling them into essentially this 2x2 matrix product, vector matrix, vector product. So, and the joint covariance matrix looks like this. Let's not do it on the spot. And yeah, so what this entails is, okay, the expectation of z involve the precision parameter. And if we just plug in the last equations we suffered through in the first part of the conditional Gaussians, we should get something like this about the conditional distribution of x given y, which are the net messy paths. So we give, in the book, they give the covariance matrix of x given y a name and then express this whole thing. So here's the result summarized. So what we've provided in real time here is merely a logic on how you might get from one to the other, because I believe this particular manipulation is not particularly interesting. Yeah, you could do it offline, but as in a lot of engineering math, staring at the results and trying to agree with it is also good enough for now. Right, so given x and p of y given x, we have essentially seen forms of p of y and p of x given y. Indeed, the mu of y is the linear form of the mu of x plus essentially two of the uncertainty term, covariance terms combined. Hence, like modulated by a, which are somewhat reasonable. The p of x given y is a mouthful. I won't try and read it out loud, but we will see it again shortly. And the reason we will see it again is we're going to use that longish term to compute the posterior distribution of Bayesian regression. So here's the setting. The notation changed again because, well, in the book, we we now have hopped from chapter 2 to chapter 3. It's not too much of a jump in terms of notation, but let's just walk through it. So in chapter 3, we've already seen this. There is like the distribution of a target given data and weights are normal, subject to a noise parameter. And the mean is the linear combination of weights and feature functions. Now, the new thing for this lecture compared to Monday is this prior distribution, that W is a normal distribution with mean of 0 and covariance of S0. So notation-wise, we would like to estimate the posterior distribution after seeing n data points. Essentially x, I, and ti pairs for I equal to 1 through n. And this is what the notation of mean sub n and S sub n means. The reason that this is written in such a way is because now we can ask questions about what if we have more data versus less data. Yes, I see a question about the mean, like the conditional Gaussians. Let me address it after maybe the next 3 slides when we would have pretty much done with most of the conditional Gaussians for today. Okay, so I'm right. Okay, the book is giving us the expression here. But let's just try and see, again, an overarching logic about how we get from what we did in the last half an hour or so to here, right? So what would be the estimate of the posterior mean and variance? Basically, it's the core question we're trying to answer. So remember, we just saw this summarized slide, basically marginal and conditional Gaussians, like essentially for linear regression, or when x and y are like this functional, like when their mean has a linear dependency with each other. So from the top to the bottom corner, the change of notation is essentially it's not the obvious way around. So x go away. X becomes W, right? Y is the target, becomes T, right? A becomes the data matrix phi. And this is implicit sort of m by m. Okay. What we are after is basically equation 2.116 correspond to the posterior of W, right? Because the 2.1515 is the marginal distribution of T. We're quite clear about that. So we do the notation change here. And we could intuitively verify at least this term. It says, well, the covariance of the posterior is sigma, where sigma is this term over here. And if applied to linear regression, it becomes this term here. So what is it? Right, so it's the original precision parameter of W, which is S0, right? Plus this quadratic term involving data of phi transpose somewhere here, and also involving the precision parameter beta, right? And the slight convention change is the this expression 3.51 is on the inverse of, well, this is essentially the precision matrix, where 2.17 is looking at the covariance matrix, therefore there's an inverse on the outside. If you put it over that inverse, this appears. So switching between the convention of precision and covariance matrix can be quite confusing, and it's
我只知道他早上一直在说要一个章程，因为好像我们的隧道停了。
Okay, I've heard someone saying something. If it's a question, then please shout a bit. Let me see if I can turn my volume up. Yeah. If not, this is pretty much the main main result of Bayesian regression. If we try and make sense of this, let me see. Okay. So let me. Right. So I have copied this equation there. So let's try and interpret this a little bit from a intuitively. Right, so this is the general prior. On top is P of W with something like normal of mean. Yeah, S0. Right, so in the general case, the mean is a function of, well, it has the S of n, the covariance matrix on the outside. We'll see about that. But the mean of the parameter is a combination of the data and target and the prior mean scaled by its variance somehow. So that's somewhat reasonable, right? For the covariance estimate, after seeing endpoints, it is basically a fixed term. So this is fixed, does not change with data. After seeing data. And the second term is data dependent. And phi transpose phi is somehow, we can interpret it as data covariance, right? With mean removed, assuming phi is centered, then the second term is data variance. The trade-off between the two are beta, which are the prediction, uncertainty. So remember, this phi is a big long matrix for if we have lots of data, which means the magnitude of the second term will grow as we have seen more data. So therefore, so this is the intuition of S of n is that it's decided. So the prior is more important if n is small, right? Number of data points is small, and then data is more important if n is large. This is, I think, a principled way of trading off the information we have from data versus the knowledge we assume we have. which is somewhat preferable. So let's look at another special case to help our intuition. So instead of saying, oh, now we have this prior as a general multivariate Gaussian, as we have seen manipulating general multivariate Gaussians, I mean, there's lots of matrix expressions that can get in the way of an easy intuition. So now we simplify. We say, well, we assume W is what's called isotropic Gaussian, basically a spherical Gaussian, where in each of the dimensions, the covariance is alpha, or 1 over alpha, actually. And this expression 3.52 is also written in a Bayesian way, so that W is conditioned on alpha. But this is just the prior. It's conditioned on alpha because alpha is now the prior of a prior, right? Terminologies aside, so this allows us to simplify the posterior mean and covariance into something that's easier to reason. So plug this in here, and then we simplify this. So now, the posterior covariance matrix is beta times data transpose. It's still a trade-off between the identity matrix and the covariance of the data, which is somewhat intuitive. The mean vector is now, okay, beta times this term, like taking the inverse, right? Taking the inverse and plugged into the middle. And then times phi transpose t. You say, well, okay, that's a mouthful. Yes, it's a mouthful, but it's a mouthful that we've seen before. So, right, if we do this one, we remember, I think I copied not the best equation here. The best one is the regularized one. Basically, the second term in here is essentially the normal equation, the unregularized normal equation for the maximum likelihood. The mean of the posterior for weights goes back to the normal equation. Moreover, okay, this next slide has the right equation on. In here, we are repeating the mean and covariance of posterior under isotropic mean, and then down the bottom is this maximum likelihood estimate of W using a regularization parameter lambda. So it turns out that these two equations are equivalent if we just swap call alpha lambda. What this means is if we take the log of posterior probability, it is a sum of likelihood and a sum of prior because of Bayes' rule. And for Gaussian likelihoods, if we expand them, basically we take the log of the likelihood at x and log cancels out, it boils down to these two quadratic terms that one is the sum of the square error, the second one is the regularizer. So if you have been practicing and like regularized least squares in, let's say, deep learning regression tasks or in IML, then the Bayesian view provides a theoretical and principled mathematical basis for it, rather than saying we just don't want W to blow up, right? So this is a step, I would say, a conceptual step forward from chapter 1 of the PRML book, where we just say, well, we looked at W is too big, I don't like it. So let's add a regularizer term. And here, what we're saying is, well, this is equivalent to expressing the prior of W as an isotropic Gaussian with parameter lambda. And we can, reason about whether we want the prior to be broad or narrow. All right. So with this, let's look at this picture, and then I'm going to answer some questions. So what this picture says is it's basically a graphical illustration on how the different probabilities change when we see different data points. So the first row of plots, right, there is no plot on the left for a good reason, because we haven't seen any data point yet. So this middle plot is basically says the prior of W is isotropic Gaussian. Between -1 and 1, there are a big ball of uncertainty. And if we just sample different vector W from this, and W is two-dimensional, from this space, so in this case, we are looking at regression functions of right here. Basically, y equals W0 plus W times the scalar x. If we just sample W1 and 0 from this ball of uncertainty data point here. And we run essentially the Bayesian estimation mentioned on this page. Essentially, you plug in one data point as 5, it will be a vector, and compute the data likelihood. It looks like this. The posterior probability of W gets narrowed down a lot. Right, okay, surprise. We get information even from one data point. Now we have 2 data points. So all the lines we sample tries to sort of pass through these 2 data points, and the posterior probability of W, again, narrows down a lot. So this first column of plots basically evaluates like what, P of X given W, right? Oh, actually, is P of Y in this case. Different notations. So P of Y given W and X. But in here, they are plotted in the W space. Right, so after seeing a whole bunch of points, the posterior probability of W like shrinks a lot. And the ground truth point is denoted by plus. Therefore, after these many points that are somewhat noisy by nature, as we can see, because of the precision inherent noise parameter beta, we can see the posterior probability of W is pretty narrow, which is good. So what this approach gives us is not only the maximum likelihood estimate, which will only give us, let's say, essentially the mean after, like mean of W here, right? The maximum likelihood estimate also does not take into account how many data points we have seen. Therefore, it will have no way of distinguishing how certain we are in the estimate of W, right? So the advantage of going through all of these matrix algebra, well, after going through it once, at least for linear regression, you can plug it in. Applying it is to have like a confidence, a certainty estimate on, let's say, the parameter we produce. You could do similar things with deep learning in a variety of ways. Bootstrapping data is one, but there are other ways as well. variation autoencoder, things like that. Let's not go there now. But basically, you have seen one instance of Bayesian estimate that gives you something more. So let's get to the questions. I'll just. How come? So Vikram asked, how come mu of A is the mean of? It's the mean of from the joint and not. Right. And not about the marginal. So, good question. It's actually both. What did it mean? Let me go back there. This slide. So mu of A. So it basically says if I have a long vector where the first chunk where I write denote mu of A as the mean of the first chunk, it is also the mean of the marginal distribution, which should not be assumed in general, but it is true for Gaussians, no matter what the covariance is. Does that make sense? I'll leave it at that. And move on to the next question. Fei Yang asks, Bayesian regression. Oh, great, thanks, Vikram. Fei Yang asks, so Bayesian regression is equivalent to the maximum likelihood solution for the regularized least square error. Yes, that's correct. Xinyu said, how could we determine the values of M0 and S0? Good question. Let me read your next question. Why do coefficients W obey Gaussian distribution? Good question. Right. Yes, let me answer maybe the second question first. So why are these different things Gaussians again? So we kind of made this cheeky assumption in the beginning. Now let's revisit it. Basically, if the variables are Gaussian and the prior for the mean are Gaussian, the posterior is also Gaussian. So we like it. And we call it conjugate prior more generally. And where do we assume that exactly? So roughly in the conditionals. Let's see, this one. Okay, this is a good overview slide. To restate that, we assume that. Right, so as we did in the change of variable slide, this P of X is essentially the prior, P of Y given X is the data likelihood. Because of the conditionals and marginals of multidimensional Gaussians and Gaussians, this posterior thing is also Gaussian. I hope that makes some sense to you and others. And your first question, yeah, how do we decide on M0 and S0? That's a great question that do not have one simple answer. Here's the cheeky answer, which is we just showed that these prior, at least for example, for isotropic Gaussians, the variance of the prior distribution is your regularization parameter. For a lot of you who have practiced hyperparameter search, you know what to do. I think the Bayesian way is that it should represent your knowledge for the domain. If you're not sure, what this picture tells you is that you've set a sufficiently broad variance parameter, and the data will help you out if you have some data pretty quickly, as we can see. And I hope that helps. There is a thing called non-informative priors, but it's usually, right, just specify a broad like distribution if you're not sure. Okay, that's so thanks, Qingyu. Jin Hong asked, by the way, there's no silly question in this class, so ask away. How Bayesian regression actually is the same as maximum likelihood? Right, good question. Let's go there. Yes, you're very right in catching that. In Bayesian regression, we compute the posterior. The equivalence, I kind of didn't cover this slide fully. So if we maximize the posterior, the mean of the posterior estimate is the same as the maximum likelihood estimate from from the frequencies estimate MLE with a regularizer. In Bayesian regression, this uncertainty term, the variance after seeing n data points, is something we get as a bonus. I hope that makes sense now. Okay, we're all ready for 13. What do we need to do? Oh, right, okay. So I'm gonna move on, if you guys don't mind. Right, let's not try to manipulate this, but let's, we talked about predictive distribution briefly in chapter 1. Remember this picture, right? We keep seeing it. Basically, once we've estimated a prediction function, the distribution, at each point of the function, there is also a distribution, right? Determined by this beta parameter, noise parameter. So in this lecture, what we have is not one prediction function, but sort of a whole bunch of them sampled from the posterior. So what does that mean, right? It means this. Again, the notation is a bit, there's a bit of notation to digest. What it essentially means is we take this target distribution using Bayes' rule, like multiply with the posterior of the parameter, and then integrate the parameter W out, right? So we know what the posterior is. That's what we spent most of the past hour. The first part is just that Gaussian in this picture. We plug both of them in, and now we finally find a use for this long expression, which is the marginal distribution of the target, which is a bit weird, right? It's essentially that expression plugged in, and we can compute a form of like P of t given the data, and the variance and noise parameters and the targets. And moreover, we can also quantify the uncertainty around the prediction using more than beta, that is, right? So beta is one part of it, but data also comes in, right? So this is a richer expression of the uncertainty around my prediction. So what does this do? Graph pictorially, this. In chapter 1, we've seen a picture that's sort of like the last picture on this page, where we have this pink cloud of uncertainty. That is essentially a tube around the sinusoid we're trying to fit. In this particular case, so these pictures, they don't exactly correspond, but it's fitting the sinusoid with 1 data point, 2, and 3, and 4. Well, to 1, 2, 4, and many data points. So as you can see, because the cloud of uncertainty actually depend on the data, it actually changes with respect to X, which is nice. And we can also sample from the posterior of W, which gives us initially essentially curves that are all over the place. And then after a lot of data points, they look like the sinusoid. that we're trying to fit. So that's nice. Yeah, okay, the page flip is rather slow on Teams. I hope you got some of that. So do we want to be doing this a lot then? One thing to consider is the curse of dimensionality for high-dimensional Gaussians. What kind of high-dimensional Gaussian are we talking about? We're essentially talking about the dimensions of W. If we're using let's say if our input is a mere 2 dimensions, but we're using, I don't know, 10th order polynomial kernel on them, then that translates to a W of however many, yeah, actually 20, or is it, no, 10 choose 2, yeah, a lot more than 10 dimensions. Suffice to say that, right? So for those of you who have taken databases or other CS courses, the curse of dimensionality in discrete space is probably not a strange concept. Basically, if I want, right, if in 1 dimensions, I partition my continuous space into 3 buckets. In 2 dimensions, I have 3 squared. In d dimensions, I have essentially 3 to the power of d. So that, yeah, there is an exponential blow up here. So in continuous space, the intuition is less, well, it requires some more thinking. Basically, if we consider a sphere of radius r equals 1, what is the fraction of the volume of the sphere in a d-dimensional space between r equals 1 and r equals 1 minus epsilon? Basically, the point is to show that most of the volume in high-dimensional space is actually concentrated in the thin shell near the surface. The inside of that high-dimensional ball is almost empty in a sense, which is strange. That's why, like, we as people are not conditioned to think correctly in high-dimensional spaces. The most we can do are about 3 dimensions. After that, some of the intuitions break down. So to do this, what we need to do is to apply the formula of the volume of spheres and plot it out, right? So for d equals 20, so most like 90% of the volume is concentrated in like less than 0.1 distance from the surface of the shell. Like it's even sharper for even higher dimensions. So corollary of that, I won't derive it here, is that in here we're plotting the probability density of with respect to radius of a Gaussian for various values of this dimensionality. So for Gaussian, these bell curves, we kind of think, right, okay, most of the probability mass or probability density should be around where the mode is at the center, right? That is correct for 1-dimensional Gaussian. It breaks down for 2-dimensional Gaussian, like isotropic Gaussians, there are even 2 dimensions. That is because, right, so this empirically we can do this. Basically, now we look at the radius as a new parameter and integrate out basically the angle parameter for isotropic Gaussians. Turns out that almost no probability mass is at the mode. For 2-dimensional Gaussians, the intuitive understanding is that despite the mode has a high probability density function, there's only one, like, in a sense, or loosely speaking, one single point there. But if you move away from it, there's a sort of a circle of different size around there. So despite the value of the PDF being smaller, but if we integrate around the curve, in total, we get a bit more probability. There is a peak value. The strange thing for high dimensions is that this peak moves away from the origin pretty significantly. And I believe for very large d, also the variance decreases. Therefore, we can see this in this expression down here. The variance is basically 1 over R. Is it? Oh, sorry. No, this is not a Gaussian. Basically, it's R times the exponent quadratic function. So in high dimension, really high dimensional Gaussians, the probability mass is actually concentrated in the thin shell, somewhere away from the origin. So that can be problematic. So what this means for fixed basis functions and trying to do Bayesian inference on them is the following. So there are pros and cons. The pros include, well, if we assume a fixed set of basis functions, we can get closed form solutions to the regularized least square problem. And also there's a tractable Bayesian treatment, right? I just tell our computers to do all the linear algebra for us. Then we get the full Bayesian treatment, the mean and covariance matrix. That's nice. And well, if our basis functions, we have like enough of them and they're sufficiently expressive, then we can model arbitrary, well, any function between the input and target. And that's very nice. Right, so the cons of this is that we need to decide on the basis function before we, like, if our data set is growing, we need to just decide the basis function beforehand. I'm hand waving here, so there's this statement I'm not going to fully justify. Is that sometimes the number of basis functions needs to grow rapidly, often exponentially, with the dimensionality d. So you may be able to relate this because we talked about curse of dimensionality. Right, so there are some fixes for this. For example, neural network combined with Gaussian basis functions. And we can also view neural network as learning adaptive basis functions. And there's also SVM, which for some of it, the basis functions are implicit because we're working in dual space. So these are, I guess, criticisms that hopefully leads to teasers for subsequent content. Okay, we're sort of 5 minutes away from 4:30. But I do believe you want to hear about Chao divergence. So Jin Hong, yes, log of prior serves as a regularizer. That's correct. Right, Alex is here. That's great. Thank you. I just saw that. Right. So I'm just going to give you a teaser about information theory, which is around the end of chapter 1, because Alex made you work through it. There's this, the beauty of information theory is that there is this somehow deeply philosophical question about how much information is in a random variable X. The design of, well, information started from Klaus Schennel, who derived this, yes, published it in 1948. Well, intuitively, so it quantifies the degree of surprise on learning the value of random variable X. Say we want this to be a function called h of X, right? So intuitively, so if, let's say, if we are dealing with a coin flip, if the coin is fair, we are probably least surprised if we turns like heads or tail because it's equal probability. But if the coin is highly biased, let's say if it's 0.9 probability of turning up heads, then we kind of have a strong expectation going, like we have not a lot of uncertainty about the outcome. And therefore, the knowing the outcome probably don't convey as much information as the fully fair coin. So the assumption here is, let's say for discrete P of x, H of x is monotonic. If there are two random variables that are unrelated, we want to claim intuitively that the amount of information we get from both is the sum of the information for each of the random variable. So for discrete x, here's the recipe for information entropy. It's the expectation of the minus log of px. This is a mouthful. Let's just apply this formula to a number of simple cases and see what we get. Right, okay, so consider now not a coin flip, but an 8-phase die with equally likely states. This h of x function is end up being 3 because the probabilities are all 1/8. And then each of the terms in the summation are equal, so therefore there's 8 times in front. So because the log is base 2, this thing is called allocally named bits by Shannon. If you recall your essentially digital logic class, how do you represent 8 states in binary digits? Well, 3 bits, right? And they're written out here. So now consider the case where there are 8 possible states, but they are not equally likely. And the probability of each state looks like this. So what is the h of x function now? We can just write it out, right? We write it out and then compute the value. It says 2 bits. One observation is that when the distribution is not equal, the amount of surprise we actually get, it actually decreases. And you wonder, right, what does 2 bits mean? It means actually this particular random variable, its state can be encoded in a set of codes that are of unequal lengths. And on average, we get an average representation of 2 bits, meaning when we're less surprised about a particular random variable, on average, we can actually transmit less information in order for people to learn about their value. So this is cool. This is one of the main results in information theory. The entropy is a lower bound on the number of bits needed to transmit the state of a random variable. And Shannon worked at Bell Labs, which are like lots of where communication technology are developed. So these, yeah, that's the origin of these particular concepts. So graphically speaking, if we have essentially histograms of discrete states that are a lot more concentrated, entropy is lower than the histograms of random variables that are spread out. So you can read a book about whether this name entropy connects those in physics, connects to those in physics. It does. And also, an anecdote is that, well, von Neumann recommended to Shannon that he uses the term entropy, not only because it is similar to the entropy in thermodynamics, but also nobody really knows what entropy really is. So any discussion you have always have an advantage. Well, I think this is a good wisdom about naming new things if you do come up with some later on in your career. So you may say, what about entropy for continuous variables? I'm not going to derive it. It's basically going back to calculus in the book. There's a few pages on that. For now, we're just going to say we replace the summation sign with the integration sign. and keep the minus log fixed. And here the log base changed to E, and the unit of this is called nats rather than bits. Another conclusion observation that's worth mentioning, and we won't go into here, is basically for continuous distribution, if it's a proper distribution and has a given mean and variance, what is the distribution that maximizes the entropy? The what's called differential entropy up here for the continuous distribution. So the answer is no other but the Gaussian distribution. You can show this without too much difficulty with by plugging in Lagrange multipliers that we showed last time around, and also completing the squares for Gaussians. In this case, it's just scalar. So also look at the book for this. Before we introduce Chao divergence and mutual information, the two other important concepts in information theory, it's worth going through this thing called convex functions. Also because it's going to appear again later on in this class in a few different shapes and form. And plus, I think Anthony Pena also started a Piazza thread on why are we just taking first order derivatives and assume all of these stationary points are maximums and minimums, are maximum equal solutions. The answer is actually here. So I think Alex and Josh jumped in and answered that thread fully. But for those of you who haven't read it, there has been lots of Piazza posts, is because the functions we have been looking at are convex. When they're convex graphically, in low dimensions, they look like a ball. And if we minimize, let's say, mean square error, there is a unique minimum. They look, and they are, let's say, easy to find if we do gradient descent. In our case, we don't even need to do gradient descent. So the technical definition of convex functions are as follows. The geometric meaning of that is that the chord connecting any 2 points on the function sits above the function itself. It's expressed in 1.114. Basically, the function value at this point, expressed as a linear combination of the two input values, is always less than, sits below the linear combination of the function values, which is the blue line. Right. So this particular thing, if we generalize this beyond just linear combinations 2 points, it leads to Jensen's inequality written in a couple of different forms that are written out here. So great question. Okay, so thanks, Alex, for answering things in real time. So I just move on. Maybe we can see what questions we have left. So basically, when there are not two lambda, like one lambda, one minus lambda, is a whole bunch of lambdas that sums to one. Well, the function value of the convex function still sits below the linear combination of the function values. And if we now treat these lambdas as essentially discrete probabilities, then we can replace the sum with the expectation. If we now take the leap towards the continuous random variables, it's basically the function of the expectation is still less than expectation, less or equal to the expectation of the function. All right, and let's use this. So Chao divergence is the quantity that sort of measures the difference or between two probability distributions, Px and Qx. The intuition is that if we have, the intuitive question it tries to answer is that if we have incorrectly represented Px with Qx, how much more information do we need to recover P of x? The mathematical expression is, so you can spot shadows of P, like this bottom part is essentially the entropy of P of x. like in here, the top part is the cross entropy. Basically, well, Qx is in the log, but the expectation is taken over P of x, subtracting the entropy of P of x. Okay. So this is not a, it's not symmetric in P and Q, as hinted in this question, and it's not a proper distance measure. So we can show, using Jensen's inequality there, that the Chao divergence between P and Q are always non-negative, and it's only 0 when P and Q are equal. So that's nice, right? So it's sort of an intuitive measure of how different two things are, despite it doesn't have the formal qualities of a distance metric. So I would like to summarize what we saw in this whole section with what's called a Venn diagram of information. And on this slide, we're also sneaking in another concept that's half new, basically conditional information. If there are two random variables, how much more information do I get if I already know X, how much more information do I get from knowing Y in addition, right? So this is a bit of a painful. So the definition, yeah, it will make sense after you spend a little bit of time with it. And we can define basically the mutual information between two random variables X and Y using conditional information and the entropy information, entropy of the joint distribution. So before all these sink in, it's more intuitive to look at what's called, what I call the Venn diagram of entropy and information. If we view the entropy of a random variable is always non-negative, right? So we can draw it as a circle. H of x is red, H of y is blue. The conditional entropy are actually the diff part of this Venn diagram. The entropy of the joint distribution is the union, and the mutual information is the intersection. And it checks out like mathematically as well. So that's all for now. I think we went about 9 minutes over, and I know you do want to hear about assignment 1. So let me just scan the chat. Yes, there's some discussion about concave functions, and I assume Alex has mocked up all the question. So let me just stop sharing the slides. Do people, okay. So thumbs up if you want to just keep this recording rolling, I guess. Give me some other emoji if you want the assignment to be in a separate recording. Okay, I'll just keep it. Well, one. Just pull up the assignment. So my screen is trying to share itself. Bear with us. Still going. Okay. Just share the whole screen. Teams is slow. Oh, okay. It's shared now. See yourself. Let's blow it up. So here we go. this assignment has 3 big questions. The first question is a warm-up. And I thought it will be like interesting to do a probability exercise in a psychology context. So basically, Kahneman and Tversky, actually Daniel Kahneman won the Nobel Prize in economics for some of their joint work. At that time, Amos Tversky is no longer alive. Otherwise, he would probably have won as well. So they give people a probability question like this, for which there are official answers available. If you do the calculation, but they've shown that more people's hunches are wrong than those that are right. So in this case, there are 2 models, right? So one model has boys are majority, the other one is boys are the minority. And if we have 2 classes of equal size and observe a fraction that's right in the smack middle, which one of these are more likely? So you can take a guess and then do the calculation. And then you could also, right, without doing the calculation, reason about which one is more likely. Things, right. So things like, oh, if I have a class of reasonably large size, what the probability distribution might look like will be useful. So there's that. After that, hopefully you have some new appreciation about whether human hunches are reliable probability guesses or not. So there's a whole library of work along these lines that Kahneman and Tversky did. I saw, well, they are good source of assignment questions, which I can use on people in exams and next year's. All right, so that's that. Let me pause and ask Alex if he wants to talk to problem 2 or 3, or you prefer me to do most of talking where you jump in at the end about code and geometry.
I can talk through it if you want.
Yeah, so go ahead. Let me know if you want me to stop screen sharing or if you want me to scroll, if I haven't scrolled.
Right. So I guess for the other parts of the assignment, I'll talk about section 2 specifically. It will be, I guess, a bit more technically challenging than the first part. And there's got to be quite a lot of narrative text and I guess lots of, little bits, which is just trying to contextualize a lot of the questions. But hopefully that won't put you off too much, because I guess in essence, what we're trying to show, at least what we're hoping to show with this question, is to demonstrate how this family of distributions called the exponential family, and how this kind of generalizes a lot of other distributions you may have seen before. And hopefully we'll be able to also show that these family of distributions also have really nice statistical and kind of geometric properties as well. So I guess that's kind of like the overall aim of this question. But of course, we can't show you everything. We need to make you guys do some work. So for a lot of the questions, there's got to be a lot of, there's got to be some computation you're going to have to do. So I guess, for example, for question 2.1, it's fairly standard, hopefully, where you just need to kind of show this is a valid PDF. And then as we go down, we're trying to, increase the complexity a bit. So I did key into the lecture a bit earlier, so I did see how you guys were doing kind of this Bayesian linear regression stuff. So hopefully there'll be similar, this next question, so 2.2 and 2.3 will be similar in nature, where you're kind of using Bayes' theorem and you kind of need to just go through the algebra. And you'll hopefully see that there are some quite neat properties which actually pop out when you consider an exponential family distribution as the prior with the normal distribution. So I guess scrolling down a bit as well. Right, so there's Also, just a note in this assignment, there's some questions which are for 8600. Of course, undergraduates are free to attempt these questions as well. And if you do better answering all the questions, you'll actually be credited better as well. So there's like a marking scheme. But apart from that, so similar to how there was like a question in the chat, which kind of was talking about how the map estimation kind of reduced down to regularization, you'll find in machine learning, there's a lot of these similar concepts where you have like this one idea on one side and another approach, which maybe looks maybe intuitively similar, but is quite from a different angle. You'll actually find that these approaches kind of connect in a nice way. And this is one of the questions, I guess, where maximum likelihood estimation is equivalent to KL minimization. So this is just kind of one of the neat tricks. And there's some even more nice properties you can show if you consider exponential family distributions. Okay. So yeah, there's quite a bit of text between this question and next. So I'll just speak of it broadly. But for question 2.5 and 2.6, well, it's essentially all working towards figure 1 to try and prove figure 1, which is you can think of it as like a Pythagoras theorem, except for KL divergences. So intuitively, maybe it would look kind of similar if you like print it out on a piece of paper, but there's some mathematical details you're gonna have to work through. And 2.5 is kind of the key lemma which lets you prove this result without too much difficulty. So I think a lot of the work is got to be in 2.5. But hopefully this is like one of the nice geometric properties you'll be able to discover and prove with exponential families. Lixing, is there anything I should say about question 2?
I saw, right, so some of the mechanical things that you're expected to do is, right, so wrap your head around the notation for the exponential family. It's slightly different than the one in the book. And then, for example, question 2.2 and 2.3. 2.2 is echoing this lecture, basically conjugate itself. And 2.3, in the book, there's already a reference of how we express normal distributions as exponential families. And once you have, right, 2.2, then 2.3 should not be too difficult. Same thing goes with 2.5, which is expressing Chao divergence in this set of parameters of the exponential family, which we hope is hopefully clear enough after reading the question carefully. And as Alex said, most of the work goes in there. And after that, 2.6 should be somewhat easier.
Oh, right. Also, another point in terms of notation, feel free to like, I guess, search up stuff on exponential family distributions outside of the textbook and outside of the assignment, but just do be careful. So the notation we're using in the assignment is following the Bishop textbook, but that notation doesn't actually follow a lot of what is typically used. But we just wanted to set it out this way. So in case you're only reading the textbook, everything will more or less align with like the smallest difference.
Yes, it's worth talking about the difference as well. So yeah, a lot of things, most things we saw in this book can be expressed without the h of x term. But right, so this new style of eta term is essentially the minus log of the g of eta term in the book. And hopefully after you work through the question, you will appreciate just writing it this way rather than the other way is convenient. Somewhat analogous to the way we sort of keep switching ourselves between the covariance and precision matrix today. There's right one way of notation that's good or more convenient for the particular task you're doing. And it can be hard for people who are new to this area, but it's right. Just be careful with the manipulation, and it should work. So I hope that's it for question 2, which do not require coding. Now we are not done with exponential families yet. Question 3.
Yep. So I guess the first part of question 3 is hopefully somewhat familiar. Essentially, it's just instead of Gaussian mixture models, which you've hopefully seen before, we're just replacing the Gaussians with exponential family distributions. So there'll be slight differences, but I think a lot of the derivations will be actually very similar. So my recommendation, I guess, if you're not quite sure where to start, try and look at Gaussian mixture models, which is a lot more common, I guess. You'll be able to find it in other places, but I don't think you'll be able to find too much on exponential family mixture models.
Right. So I think this is a useful exercise. So in next week, Wednesday, we will be talking about EM and Gaussian mixture models to some extent. In the course schedule, we actually said that you're expected to have read Gaussian mixture models and K-means as prerequisite from both the PRML book and the MML book, whichever version right, that you're more comfortable with. And next Wednesday's lecture, we will devote our time to essentially what we call the second and third view of EM expectation maximization for Gaussian mixture models. And this particular question appeals to the second interpretation, which is right, the joint likelihood and the conditional of the hidden variable Z conditional data. So if it doesn't make a lot of sense now, hopefully it will roughly the same time next week. If not, ask us questions. Yeah, we'll have an EM tutorial as well, which I think is somewhere nearby. Right, okay, so the first question is to derive the expectation step. The second question is maximization step for exponential family, and then implement it.
Yep.
So for your convenience, or so people may have different places that they are more comfortable to start. So yeah, Alex, Shamin wrote this, designed these questions, and they have provided the recipe for the implementation, where the more theoretical questions are just asking you to prove them. So you could start at question 3.3 as well.
Yep. So I guess if you're more comfortable coding, I would probably recommend you start at 3.3, and I think it's also 3.6 or 3.7. There's another coding question at the very end as well. So these questions, they don't require you to do any of the theory stuff, and I think they're worth 30 marks in total. So it's a good chunk of the assignment. So those are definitely good places to start.
Yeah. Okay, so we talked about Bayesian linear regression, and the notation here is largely the same as what we saw today. Now the rest of this task, right, so the 4670 students are only required to do the implementation, but 8600 students are right. So you're expected to derive this as well. So basically, how do we use essentially this new recipe EM to derive what we just did today, Bayesian linear regression? The gist of this question. And again, it's broken down to the E step, to the M step, broken down into 2 parts. As you can see, there aren't, or like there isn't a lot of points associated with these 2 questions combined. So there's this, and then wait. I don't know if it's worth talking about the code. Where's my Jupyter notebook? Right, Right, so basically the Jupyter notebook provided with the assignment is basically a shell for visualizing your results. What people are expected to write sits in I'm looking at the wrong file text editor as well. Is there any like things that worth mentioning about the code and notebook, or people can jump in with questions?
I guess just for the code and notebook stuff, it's probably so there's a few files. So the current file which Lishing's going through, you don't actually need to look at this one at all. It's just framework code, but there's two files, one for each question, which you'll be required to fill in. There's, I guess, like function or areas where it's clearly denoted to fill in stuff. And I guess those are all you need to do. Do make sure to use the, I think it's like called implementation viewer.ipython notebook. So that is going to be, that's like a good way of kind of checking if your solution is doing the correct thing. So everything should kind of work as expected. So in terms of the EMM question, you kind of should be able to learn these Gaussian distributions. And for the Bayesian linear regression, it should kind of like learn the correct line. And hopefully the visualization is clear enough for you to see what to do.
I'm going to ask you a question, Alex. If people wish to debug
Yes.
what they did, yeah, right, you'll probably end up needing to modify the IPython notebook file. But if when we grade, the auto grader will work off these question Python files. But the tutor is also going to look at are we expecting the notebook to be submitted?
Yeah, so we are expecting a fresh copy of the notebook to be submitted with your code. We'll outline some more details once we have Gradescope up and running. But feel free to like just copy paste and make a new file, like a copy of it, and then edit it as you wish. I would probably recommend doing that. And that way you can kind of play around with the code, like print out, and debug, print out intermediate values. But yeah, we'll send a reminder about submission stuff as well. But do, I guess, keep an eye out on Piazza and just, I guess, keep that at the back of your mind.
Right, so there has been two more questions. I'm looking at the chat. Fei Yang said, can you show an example of using the Lagrangian multiplier? The short answer, I know we are kind of over time, is showing that the Gaussian distribution maximizes differential entropy in the book is one example. There are others scattered through the book, which we can ask us later. Xu Yang asks, are there any reference book / source that we can get a clue from about the notation in Assignment 1, especially the exponential family part?
I don't think there's going to be one unified source, unfortunately. So I would definitely start with Bishop's textbook, since that is what we're kind of working with. We'll have the closest in terms of notation-wise. But apart from that, you could possibly look at the Wikipedia article, but it will have pretty much anything which isn't in the assignment, as well as being in the Bishop's textbooks. They will be different, I guess, notation. So for example, unfortunately, the eta parameter which we're using in the assignment, that actually means something completely different usually. which is something we also use, but I had to relabel it so to keep consistent with the textbook. So definitely start with bishop, since the notation will more or less match. But afterwards, you could probably start with the Wikipedia article or any of the, if you just search up exponential family distributions, there'll be quite a few lecture notes which you could look through, but just be mindful for notation.
Yeah, I agree with that. What I came across recently was Michael Jordan in Berkeley has a textbook which has a chapter in exponential family that has a bit more content if you desire, but we don't necessarily really need it for assignment 1.
Yeah, I guess along the same thread, so someone, Mahiro, asked about if we're able to solve everything in assignment 1 with the material in the course. I think that the answer is definitely yes. So a lot of it looks kind of complicated, but when it comes down to actually like proving or like going through these questions, all you'll have to be using, I believe, even for question 2, which is probably the most theoretically demanding, is kind of just a bit of calculus, some parts of minimization, so just knowing how to minimize stuff, and then a lot of just rearranging with like Bayes' theorem, or just rearranging vector equations in general. And I think those are really the only things you really need to do. So it's kind of complex in like the in the concept, but I think solving a lot of the questions, if you kind of just crunch through the algebra, it won't be as complicated as you might think.
Cool. Alex, do you want to take this one? Jin Hongni asks, would it be possible to have a bit more hint in question 2.2, which is now on the screen? I can't see how the hint provided helps with the question.
Right. Let me try and remember. Oh, right. Okay. So I guess the other hint, which you would want to use this, since it's kind of like working with likelihoods and priors, you're going to have to use Bayes' theorem to get the this posterior distribution. And because of that, you're going to have to solve some intermediary, or like find some intermediary distributions. And that's why the hint is there, because you might need to integrate some stuff to get certain distributions. But the hint's just to stop you from trying to solve it completely. You can actually just leave it as an open integral. But I guess that's just contextualizing the hint. As an actual starting point, try and work with Bayes' theorem, and just try and expand everything out and try and simplify. That's probably enough of it.
That sounds good. Okay, Jin Hong is happy. Everyone else is somewhat happy. Stop the screen sharing.
But yeah, nevertheless, if you have more questions on the assignment, just feel free to ask it on Piazza, and I'm sure myself or one of the other tutors will make our way through it.
We'll stop the recording.